In equation 1, I is the total current generated with the application of any potential. Consider the condition when the surface concentration is in equilibrium with the bulk concentration at E equilibrium. So this equation number 1 can be rearranged in such a way that the current is 0. So this component will be equal to this one, and we get the equation number 4 as shown here, which is showing the ratio of the two components which are equal to the oxidized or reduced species bulk concentration, and the potential has been changed from E to E equilibrium. So now multiply the equation number 4 with minus alpha in the power terms, we get equation number 5, and also multiply the equation 4 with the minus of 1 minus alpha. So here we get the equation number 5 with the multiplication of this term in the power of equation number 4. Now closely observe that in equation number 3, which have been derived from the division of total current with the exchange current. So here we have two terms which are also given in the equation number 5 and 6. So we can rewrite equation number 3 by replacing these two terms with the values given in the equation number 5 and 6. Now observe closely that by inserting the values of these terms from equation number 3 as shown here, so these terms given in the brackets are replaced using equation number 5 and 6, and now we have get the equation number 7. That is the pretty big one. So here we have seen that the power terms have some common terms which can be cancelled out, in which the common terms are the standard electrode potentials within the power terms. So here we with the simplification we will get the terms that is E minus E equilibrium is the overpotential that will be represented as eta. So here one thing is to be noticed that I have put the value of plus alpha term using the equation number 5, which is the minus alpha term, as in equation 3 the factor in the bracket is having a plus alpha term. So in both components, that is the first one is this one and the second one is this, in which we can cancel out the power term containing the standard electrode potential, and we will get the remaining factor that is multiplying with this concentration ratio, that will be actually the E raised to power minus alpha and F. E minus E equilibrium, that is known as overpotential, will be represented as eta. Similarly, this explanation is true for the second component, in which we will have the power term as E 1 minus alpha NF E minus E equilibrium over RT. So here we get equation number 8, which is describing the total current over the exchange current in terms of the overpotential. So now we can again rearrange this equation as total current is actually equal to the product of the exchange current and the factor given in the bracket having two components. Now we get the equation number 9, which is known as current over potential equation. And this equation is a fundamental equation which have been used in electrochemistry, and it's having various advantages which can be explained using the graphical representation of this equation. So I'm going to draw the graphical representation which is showing the anodic and cathodic components. So here in this equation number 9, the first one is showing this component is showing the cathodic component, whereas the second component is the anodic. So the behavior of current potential, that is the current over potential equation, is given as in this graphical representation, which is showing the solid line, that is the actual measured current using the application of eta in negative and positive ranges. And this solid line is the sum of the anodic and cathodic components, as with the equation number 9, which is showing the total current that is including the cathodic and anodic component, whereas the true cathodic component is shown as this red trace that is going to maximum. Here we can see the maximum contribution to this equation is due to the only cathodic component. So this here the contribution of anodic component is minimum, whereas in opposite direction this one is the true anodic component, in which at maximum value the contribution of cathodic component is minimum, but here this line is showing the sum of the cathodic and anodic components. So here we can see that the when the total current is 0, there is some cathodic component and some anodic component. There is, so it should be symmetrical. So these points where the cathodic and anodic components are equal but overall current is 0, so this amount of current is known as I naught. So again here we can see that at large positive over potentials the cathodic component is negligible and IA is essentially the same as the total current. For the large negative potentials, the cathodic component is contributing totally to the total current. So here we have observed that if we are going to either direction, we are observing that the current is increasing exponentially. That is due to the exponential terms given here. And at extreme eta, the current level is leveled off, that is beyond to the exponential rise of the either cathodic and anodic components to leading to overall current. So here the leveling of the current is due to the limitation of the mass transfer. It means that the Oxidized or reduced species at the bulk of the electrode are involved in this current overpotential behavior observed here, and the bulk species present in the bulk of the solution or the electrolyte are not involved into the this heterogeneous redox kinetics that is occurring at the surface of the electrode. So as these new species are not in equilibrium with the species present at the surface of the electrode, so the heterogeneous kinetics have been reached to a maximum value utilizing the all the species present at the surface. So the current is observed to be leveling off, that is due to the limitation of mass transfer. If these bulk species are going to enter the surface of the electrode, that may lead to the current rise in current continuously. So these exponential factors are controlled by these factors at the surface of the electrode. If the concentration is going in the bulk is going to interpret the surface of the electrode and acting as the concentration of the species at the surface, then the concentration of this component will be increased, making the rise of the current depending on the number of the bulk species that are converted to surface species. In simple words, in this lecture we have derived a current over potential equation, which is important and fundamental equation which describe the cathodic and anodic component of the redox process in which we can observe the cathodic and anodic components experimentally, which are usually equal for the reversible processes, and overall current is actually measured by the setup, that is the electrochemical setup is actually the combination of these two types of currents. So this representation is showing three behaviors. First one is the limiting current when the total current is 0. The cathodic and anodic components have equal contribution, and either cathodic or anodic have contribution known as the exchange current. The second contribution is this exponential rise in current that is proportional to this exponential term. So when this term have been reached to a maximum value, for example at these points, now the leveling of component will be controlled by this component. So if the concentration in the bulk will be replacing the concentration at the surface, then the further rise in the these currents will be observed depending on the either cathodic or the anodic component. So here is Cr and Cr star, that is the concentration of the reduced species at the surface of the electrode or the bulk. So here we have seen that there is a maximum current that is limited by the mass transfer, and the overall reaction has been completed. So this current is actually known as the limiting current. In next lecture we will discuss some of the approximation forms of this current over potential equation given here to derive the Tefel and Butler-Woolmer equations.